Hello everybody! Today I'm going to explain how to solve the problem F from Codeforces round 950, division 3, and in the next days or so I will try to make videos for some of the other problems from this contest too. The reason why I chose problem F for making this video is because even though it was a more difficult problem, I quite enjoyed solving it and I want to explain the solution for the purposes of learning how to solve this problem, as well as for anyone else who is interested in how to solve quickly some more difficult problems. So let's begin. We have here a rectangular field of size n times m, and we have k fountains. And in short, what we need to do is to split the field in two parts, such that all of the fountains Bob has will be on one side, and the one fountain Alice will get from Bob will also be on that side. Now, our goal is to find first what would be the maximum size of plot Alice could get if she doesn't get any fountain. And for F1, we will need to see if the area of Alice land will be higher if we remove each of the fountains. So for each of the fountains, we will need to check whether her plot will get bigger or not. For example, if this is the starting plot, if we remove the second fountain, then Alice's surface will grow, and the same for the fourth one, and so on. So this is for the second sample. And our goal is to find this out very quickly for all of them. Now, how do we proceed from here? We definitely need to get to find some ideas which will be useful for both of them. So first off, we see that k is not anywhere near as big as the total size of the inputs, so we have only 200,000 fountains. So we can start by sorting them, because now when we think about it, we can figure out for each of the lines how much can Alice go. And this can be done by having a scan through the lines from the biggest one to the smallest one. And every time we get a new fountain, which could push us to the left, we might need to concede some of the ground. Because, for example, while we could have the entire ground here, by having this 4 here, we are limited to just the first two columns of the fourth line. Now, given that we have 10 to the 9 lines, obviously we can't just simulate this for every single row, but we can use the fact that there are only 200,000 fountains, and this gives us a very important observation. Only these 200,000 rows will actually be relevant and will change the answer in any way. And the reason for why this happens is because if we stumble across an empty row, we can just use the length of the Alice surface we had from the next row for the current row too. Just like here, if we were to not have the 4, we could just go all the way to the end. Now, how do we check if any of the fountains improves our final answer? Well, first off, it has to be the leftmost one on a given line. And besides that, we will also need to check two cases. So either it's the first one on its either it's the only one on its line and the answer for the next line is greater. In that case, it will definitely bring an improvement. Or if there are at least two on the same line, we will need to check whichever will be the smaller one between the previous answer and whichever is the other fountain on the same line, like the second leftmost fountain. So here, let me show you this with some examples. So basically, if we have, I will just draw two lines for simplicity. So if we have these two lines, and let's say the previous minimum was somewhere here. So let's say we could simply have all of these covered by Alice. And we have two fountains now at, let's say, these two positions. Now, because we have these two fountains, we can see here that this is the leftmost fountain on the first line, and we will need to check if we will be able to cover more by doing that. And now when we think about it, if we remove it, then we will be able to cover more, because when we have this removed, we will also be able to use these two as well. So again, we will definitely be able to do it. Now, also, even if this one would be somewhere to the right, it will still be an improvement, just because this one was to the left of the previous minimum. So now we can simplify the condition and say that if the minimum on some line is smaller than the previous minimum, then there is definitely an improvement which can be done by removing it. And this is something that can be processed from the last fountain to the first fountain, and in order to print the good fountains, we can just use a set or any data structure that allows us to do this. And this is what I did in this solution. As you can see here, I sorted them, then I found whichever position is the smallest in a certain line. And then, of course, if this position is smaller than the previous answer, we add an improvement and we are done with this first problem. And for computing the area, we can use a similar principle, because we know at each moment the position up to which we can go, as well as how many lines that fountain covers after it. Because if there is a gap of certain amount of lines, all of them will be covered by that. Now, how do we use this in order to solve F2? Now for F2, things will get a bit complicated, because in one of the samples, for example, if we remove 4, as you can see, we get an improvement both by removing this and having these 3 places now coverable by Alice, but we also get this other place, which is also coverable by Alice. So now, in essence, what we want to do is to see how much improvement do we get out of removing that fountain below, and how much improvement do we get out of removing that fountain above. And while the first part can be computed rather easily, because we know how much we would have had if not for that fountain, and also for that fountain, the second part can be a bit tricky. And what I did to compute this is that during the same traversal, whenever I would compute a minimum on a subsequent line, for example here, well, if this were not to exist, then this would have become the new minimum. And in a way, all I did was to just find all of these partial minimums and see how much I can go with this one up to the point where I would have a definite new minimum. Like for example, for this 4, I would get an improvement of 1 because this minimum is greater than this other minimum, but there will be no more improvements when we get to 2, and its value is definitely smaller than the value here. And by the value, I mean the position on the given line, like the column. Now, how did we do this? Again, I used the same approach, but I added several more cases, because there is a case which has to be handled based on whether there are two things on the same line or not. Like here I didn't have to do it because I only needed to check if there is an improvement. But here I had to do both of the cases, as in whether there are at least 2 on the same line or not. And also, if there is no change in answer, we should also compute how much we would have lost had we not removed that minimum. And again, I compute this partial minimum, and also I keep track of the difference between the lines. Like this is pretty constant throughout my implementation. I used it several times, and also up to some extent something like this here too. But the main idea was that you had to visualize how to see in terms of the differences in between each line. I was thinking at some point maybe I could do this with a stack or something like that, but then it turned out that the approach is actually much easier than what I thought it will first be like. If you enjoyed watching this video, please subscribe to the channel, like this video and share it with your friends so that they can also learn how to solve such a difficult problem easily. And if you enjoy watching my content, please let me know if you want me to create some more content. I will also try to upload some of the other solutions for problems A to E or even G if I get the chance to also try and solve it in the end. So thanks for watching this video and see you next time. Cheers!